Welcome back. So today we're going to talk about parallel algorithms for the fast Fourier transform. So the Fourier transform is it's one of the most important tools in mathematics. And it basically lets you translate a signal from the space domain to the time domain. We're going to be talking about the fast Fourier transform, which is basically an efficient way of implementing the Fourier transform. And so because of this efficiency, the FFT has a very large number of applications. For example, in signal processing or in operations that we can do on polynomials and matrices, in like computing convolutions and filtering, in mathematics, in machine learning, and many other applications. And in fact, the FFT has been voted one of the top 10 most important algorithms of the 20th century. And so I think it's fair to say that if we did not have the FFT algorithm, then many things that we take for granted nowadays simply would not exist, right? So a lot of computer science simply is not possible without the FFT. Okay, so the FFT algorithm was popularized by these two people, Cooley and Tukey, in 1965. Okay, so they discovered this algorithm, but they weren't the first to discover it. So in fact, there have been different variations of this algorithm discovered even before Cooley and Tukey. For example, there was a variant known even back to Gauss back in 1805. Okay, so to describe the Fourier transform and the fast Fourier transform, we're going to begin with a bit of mathematics. So first of all, we're going to define something called a root of unity, an nth root of unity. So what we're trying to do is just solve this equation omega to the nth power equals 1. Okay, so of course one of the solutions is just 1 itself, but there can be other solutions. Especially if we allow for complex numbers. Okay, so in fact, the solutions to this equation are going to lie in the complex plane, and they lie on the unit circle in the complex plane. Okay, so we just take the unit circle and you break it into n even parts, and then each one of those defines a complex number which solves this equation. Okay, so all of these solutions, they can be represented in this form. Okay, so e to the 2 pi I times k divided by nth power. And then so here we have n solutions to this equation. And so for any k from 0 to n minus 1, we obtain one of these nth roots of unity. Okay, so we're going to write the, so these nth roots of unity, they differ by the same amount. Okay, so basically, if we start with this number omega n here, okay, so let's define omega n to be e to the 2 pi I divided by nth power, all right? Then all of the other nth roots of unity are just powers of this omega n. Okay, so we can take omega n to the 0th power, right? So that's going to be 1, right? And then omega n itself, omega n squared, and so on, up to omega n to the n minus 1st power. These are all roots of this equation. Okay, so now there are some important properties about these numbers. So the first one is that omega n to the nth power is equal to 1. Okay, so that's pretty obvious because omega n is one of the solutions to this equation. Okay, all right. So the next interesting fact is that if you take any k from 0 to n minus 1, okay? If you take omega n to the k plus n over 2nd power, okay, that is equal to negative of omega n to the kth power. Okay, so basically, one way that you can see this sort of pictorially. So what this is saying is that if you take any solution, okay, so omega n to the k plus n over 2 is one of these solutions, it's one of these roots of unity. So if you take any one of them, or sorry, let's begin with omega n to the kth power. Okay, so that's one of these roots of unity. And now if you add n plus n over 2 to the exponent, So that basically moves you by n over 2 solutions, okay? And that's going to move you halfway around the circle. And you see that when this happens, you're going to get negative of the value that you started with. So for example, if we're talking about omega n to the first power, okay, so like this value over here, okay? Now omega n to the 1 plus n over 2, right? So in this case, n is going to be 8 over here. So this is going to be omega 8 to the fifth power, okay? And you see that what you need to do is basically just move 4 steps, okay? So n is going to be 8 over here. So n over 2 is going to be 4 steps. So we move 1, 2, 3, and 4 steps. And that takes us to omega 8 to the fifth power. And that's indeed the opposite, okay, of omega 8 to the first power, right? And this holds for every k. Okay, and the final property is that if you take omega n to the kth power and then you square it, okay, then of course you get omega n to the 2k, right? However, this is also equal to omega of n over 2 to the kth power. Okay, so omega of n over 2, right? So this is so this omega, oops, it's hard to write down here, so let me write up here. Okay, so omega n over 2 is one of the n over 2th roots of unity. So basically that means that if you take this thing to the n over 2 power, right, then you're going to get 1 over here. Okay, yeah, so we have this fact, and as an example of this, so suppose you take, let's say this thing over here. Okay, so omega 8 to the third power, right? If you square that, you're going to get omega 8 to the sixth power. And this is one of the fourth roots of unity, right? So this omega 8 to the third power is one of the eighth roots of unity. But what this fact 3 is saying is that when you square it, you get one of these fourth roots of unity. In fact, you get the third fourth root of unity. Okay. Now the fourth roots of unity are just you know, if you take the unit circle and you break it into 4 parts, so those are the fourth roots of unity. Okay, so basically, you know, so let's see. So you got 1 over here, right? You got 1 over here, 1 over here, and then 1 over here. Okay, so these are the fourth roots of unity. And you see that if you take the third eighth root of unity and you square it, you get the third fourth root of unity. Okay, so that's fact 3 over here. All right, so so all of these facts are important in the FFT, as we'll see. Okay. But before we make use of these, let's just define the problem that we're trying to solve. Okay, so the problem. So first of all, we're going to start with the Fourier transform, and we're going to talk about the discrete Fourier transform since we're dealing with you know, discrete signals in computer science. Okay, so what we're trying to do is that suppose you're given a degree n polynomial. Okay, and the polynomial you write like this, so it's a0 plus a1 times x plus a2x squared, and so on. Okay, sorry, this is a degree n minus 1 polynomial. Sorry about that. Okay, so then the discrete Fourier transform simply wants to compute the value of this polynomial, right, for inputs omega n to the 0th power, omega n to the first power, and so on, right? So it wants to evaluate this polynomial at all of these nth roots of unity. So this is what we're trying to do when you compute this discrete Fourier transform. Okay, we simply want to compute these n values over here. Okay, now in a sequential setting, then, you know, so the most basic algorithm for doing this is that, well, if you try to compute this, you can factor a in this way, right? So you can take the a0, right? And then in the rest of this expression, you can factor out the x, and then that's going to leave you a1, right? And then you can factor out another x times like a2 plus so on, okay? So, so you can factor things this way. And then in order to evaluate a of x, right, then you see that all you need to do is you plug x into the sort of the innermost set of parentheses in this expression, right? And then that gets you a value, you multiply that by x, and then add it to the next a, right? And then you multiply that by x and add it to another a, and so on. Okay? So yeah, so there basically there are n levels of parentheses over here. And so to compute a of x, you just need to do this for n times. And so that's going to take you order n time. Okay, and also you use a constant amount of memory for doing that. Okay, so that means that if you evaluate a at one position for one value of x, that's going to take you order n time. And so here, right, our goal is to evaluate a at these n different roots of unity. And so that would just take you order n squared time if you use this basic algorithm. Okay, but the problem is that in practice, you might deal with very large n's. You know, your n's can be like millions, you know, can be in the order of millions or even larger. And so if you use this basic algorithm, it's going to take you a very large amount of time to compute these discrete Fourier transforms. Okay, so we need a faster algorithm. Right? If we didn't have this faster algorithm, many things that we use today in whether it's signal processing or computer science, we simply could not use them because they would work way too slowly. Okay, so then the fast Fourier transform is going to basically compute this not in n squared time, but in n log n time. Okay, and it's basically it's a divide and conquer algorithm. So let's assume for simplicity that n is a power of 2. Okay, so the first step of the fast Fourier transform is to write a in this fashion. Okay, so now a is you know, a polynomial of degree n minus 1. Okay, but what we're going to do is we're going to write two polynomials like this. We'll call them a0 and a1. Okay, so now both of these are going to be degree n divided by 2 minus 1 polynomials. Okay, and then a0 is going to be this polynomial, but it's only going to have the even coefficients from a. Okay, so a is defined in terms of the coefficients a0, a1, a2, and so on. But for a0, right, for this capital A0, we're only going to take the even coefficients from a, and then we're going to write a degree n over 2 minus 1 polynomial from those. And then for a1, you're going to take the odd degree coefficients from a. Okay, and again, you're going to form a degree n over 2 minus 1 degree polynomial. Okay, so the reason we do this is because we can actually express a in terms of a0 and a1. Okay, because you can say that a of x is equal to a0 of x squared plus x times a1 of x squared. Okay, so the reason this is true is because if you take x squared and you plug it into a0, okay, so then all of these powers over here, right, all of these exponents are going to double, right, and so this is going to end up being, what do we have over here? So we have n minus 2, okay? Okay, all right, so now if you do the same thing, if you plug x squared into a1, right, so then these things are also going to double, right? So then this is going to become n minus 2, right? But then we also multiply by this x over here. So that's going to put another x on top of these exponents. So these are going to become this stuff. Okay, so this is going to become a 5 over here, right? And then this is going to become n minus 1. Okay, so now you see that if you add together these two expressions, okay, then you get back exactly all of the terms of a. Okay, so this is why we have this this identity here for a. Okay, so now our goal was to compute compute a at these nth roots of unity, right? And so therefore, what we can do is instead of computing a at these nth roots of unity, right, we can compute we can take all of these input values, these different roots of unity, right? We can square them, right? And then we can plug them into a0 and a1, okay? And then, yeah, and then we do this computation. So, so this just involves computing a0 at all of these squared roots of unity. And then we have to compute a1 at the square of these roots of unity. And then also you have to take the a1 result and then multiply it by these original roots of unity, okay? But if we do that, right, if we compute at these squared values, then we're going to get a evaluated at all of these original values. Okay, well, why would we want to do this? Why would we want to compute these at the squared values? Okay, the reason is that now we can make use of these different properties about the roots of unity. Okay, so the key property that we're going to use is that suppose you take suppose you take two roots of unity. Okay, so you're going to take omega n to the kth power over here. Okay, and then you also take omega n to the k plus n over 2 power over here. Okay, so these are basically, so we're going to think of sort of taking all of these n different roots of unity and pairing them. Okay, so you're going to take the very first root of unity and pair it with the middle one. Okay, so suppose you have like, 8 of these. Okay, 5, 6, 7, 8, right? Oops. Okay, so we're going to pair so then we're going to split these in half, and you're going to pair the first one from the first half with the first one from the second half, right? You're going to pair this one, that one, and then those. Okay, so that's how you should think of this. Okay, so therefore we're going to take the kth root of unity from the first half, and then pair it with the kth root of unity from the second half. Okay, all right. Now suppose you square these two values. Okay, so what you're going to get is if you square this guy, then you're going to get omega n to the 2k plus nth power. Okay, right? So then this is equal to omega n to the 2kth power times omega to the nth power, omega n to the nth power. Okay, but omega n to the nth power is equal to 1. And so therefore, this term over here, right, we can just take that out. Okay, so therefore this is equal to omega n to the 2k power, which in turn is equal to omega n to the k squared. Okay, so basically what we're saying is that when you do this matching, okay, between these different roots, all right, if you square them, now you get exactly the same value. Okay, so originally, right, this value here, of course, is not equal to this value. Actually, they're opposites of each other. Okay, but if you square them, then you get the same value. Okay, so so the reason this is useful is because we said over here that we just need to evaluate a0 and a1 at these n different values, which are the roots of unity squared. Okay, so now there are n different. It seems like we have n different values here. Okay. However, what we can see by this property over here is that now if you take the first value over here and then you match it up with the middle value, right? And then you take the second value and then match it with the middle plus first value, and so on, right? So once you do this matching, so we're doing this matching over here, then these values become the same. Okay. So in other words, for this value, right, this thing is equal to the middle value in this list. Okay, and this value here is equal to the middle plus first value. Okay, so that means that instead of there being actually n different values over here, right, we actually have that there are only n divided by 2 different values over here, right? Because pairs of these values are equal to each other. And so this is great because now instead of evaluating a0 and a1 at these n different values, at these n potentially different values, it turns out that we just need to evaluate these two guys at n over 2 values. Okay, so now our problem becomes much smaller, right? Okay, so this is a great first step. And then one more thing is that now, so we have this property over here, right? So this basically just says that we only need to compute these nth roots of unity to the kth power squared. And then if you look at this expression, you get that if we use the third fact that we had from the previous page, right? Then you get that this nth root of unity to the kth power squared is actually one of these n over second roots of unity to the kth power. Okay, so in other words, you can write So here we've already said that these values, instead of there being n different values, there are in fact only n over 2 different values. Okay, there are these values. Okay, and now we can say that each one of these values is not just a nth root of unity squared, it's actually equal to a n over second root of unity. Okay, so in fact, there are only n over 2 roots of n over second roots of unity, and so this set of numbers is exactly equal to all of the n over 2 roots of unity. Okay, so now we can see that when you want to evaluate a0 and a1 at these numbers, it's actually equivalent to evaluating a0 and a1 at these n divided by 2 different n over second roots of unity. Okay, it's the same as evaluating this a0 and a1 at these n over 2 different numbers. Okay, so now, so let's sort of summarize what we've said over here. Okay, so our main goal is to compute this a of x, right? And so we split this into this expression over here, and we want to compute this at these nth roots of unity. However, as we saw, we do not need to compute these expressions at these n different values. Instead, you can compute these two expressions, these two polynomials, at these n divided by 2 different values. Okay, and now remember that a0 and a1, right, their degree are both n over 2 minus 1. Okay, so we're basically trying to evaluate these two n divided by 2 minus 1 degree polynomials at these different n over 2 roots of unity. Okay, so this is in fact another DFT. Okay, so this is going to be an n divided by 2 point DFT. Right, so currently here, right, we're trying to compute an n point DFT. We have n inputs, okay? But instead, we've reduced this problem down to computing 2 DFTs, 2 n over 2 point DFTs. And so therefore, we can do this recursively, okay? We can compute a0 and a1 recursively at these n over 2 points. Okay, so that's what we're going to do. We're going to compute these two things recursively, and then after we've computed them recursively, so this is like divide and conquer, right? So now we've divided, right, and we computed this. Now we need to conquer by combining these solutions that we get to these n over 2 point FFTs. And the way that you can combine them is that you can say, well, what we said is that a of x here is equal to this stuff, okay? So then we simply need to, once we've computed a0 and a1 at these n over 2 roots of unity, right, we just need to multiply the a1 value by this nth root of unity and then add it to the a0 result. Okay, and we do this for k from n over 2, k from 0 to n over 2 minus 1. Okay. Now, what about the other half of the case, from n over 2 to n over to n minus 1? Okay, so those we can express in this way, right? So we can still take k from 0 to n over 2 minus 1, except for now you add n over 2 to this. Okay, and so we're going to plug this n over 2 in everywhere. Okay, but the thing is that if you look at this expression, okay, so because we're talking about these n over 2 roots of unity, then if you add an n over 2 to the exponent, it just goes away. Okay, so this thing over here is the same thing as this. Okay, and likewise this goes away, and so these two things are the same. Okay, and now this thing over here. Okay, so now we're going to finally make use of the second fact that we had, which said that this value over here is basically equal to negative of this value. Okay. All right, so that is the FFT algorithm. Okay, so let's sort of clear this up a little bit. So the FFT algorithm is saying that, okay, so we want to evaluate this expression at these n different values. Okay, so what we're going to do is we're going to just take the first half of these values, right, and then evaluate them and then do these n over 2 point FFTs. So we're going to compute all of these values for k from 0 to n over 2 minus 1. And all of these values also, okay? And then for the first n over 2 values for a, right, we're going to add a positive, this thing positively times this a1, okay? And then for the other n over 2 values, we're going to subtract this thing times a1. Okay, so that is the algorithm. And now the time complexity for doing this is going to be, all right, so we just need to compute these two n over 2 point FFTs on a0 and a1, okay? And then after that, we need to do this expression over here. So this is going to take a linear time, right, because we just iterate through all of these n different values, okay? And then the two recursive calls are going to take this much time, 2 times t of n over 2, where t is the time for doing an n-point FFT. Okay, so then you solve this, and you know that the solution over here is going to be n log n. Okay, So this shows that the FFT is going to take you n log n time. Okay, so right, so now it's helpful to actually sort of show more steps to to expand this recursion. Okay, so let's actually show the expanded version of this recursion. So suppose you're doing an 8-point FFT. Okay, so therefore your input is going to be these 8 numbers, the coefficients for A. Right, and we said that the way we're going to do this is we're going to form this, this A0, the big A0 and the big A1 polynomials, right? And the A0 polynomial is going to have all of these even coefficients, and the A1 is going to have all the odd coefficients. All right, so that's the first level of recursion. And then the second level of recursion, now, when you're computing A0 here, right? Now, again, you're going to break these coefficients. So now the input are these 4 coefficients, right? So you're going to take the even ones out of here and then put, you're going to break this into two 2-point FFTs, okay? So that's going to involve the even coefficients from this list and the odd coefficients, right? So the even coefficients are the A0 and the A4, right? And the odd coefficients are the A2 and the A6, okay? So then you're going to put them into different, you're going to compute these recursively. And likewise over here, right, you're going to take the even coefficients A1, A5, and then put them into one 2-point FFT, and then these guys go into the other 2-point FFT, okay? Yeah, so the algorithm is over here, right? We're given a list of n different A values, right? If it's just a single value, then the answer to the FFT is, then the polynomial is simply equal to A itself, okay? So then, of course, you just return A, right? And then otherwise, we're trying to do an n-point FFT. So you're going to compute this nth root of unity over here, right? And then you're going to take the even and the odd coefficients. You're going to recursively solve them, right? So this is going to get you basically n over 2. This is a list of n over 2 numbers, right? This is another list of n over 2 numbers. And now you're just going to go through this these 2 lists, right? And then you're going to take the matching values, right? You're going to take like the first value from here and then match it with the first value from here, and then multiply it by this by the different powers of omega n. Okay, so initially we're going to take, so this thing here is initially equal to omega n to the 0th power. Okay, and then eventually we want to have this be omega n to the 1st power, 2nd power, and so on. All right. So what we're going to do is initially we're going to set this to be omega n to the 0th power, right? And then we know that for yk, right, this is going to be like this, where we add omega times this y1 value, and then for the other part we subtract omega times the y1 value. Right? And then here, this is going to take this omega to the next root of unity. Okay, so we're gonna multiply omega by this thing over here, and that's going to produce the next power of omega. Okay, so it's going to go from like here to here, or from here to here. All right, so then we're going to iterate through these 2 lists, right, and use these k numbers, and then just match them up, and then that will produce a list of n numbers, and that list of n numbers is what we return to the calling function. Okay, so for example, over here, right, after you do this, after you compute this 2-point FFT, you get 2 numbers, let's say y0 and y1, right? And this is for the 0 part, right? So this is for the first FFT over here, first recursive call. And then here you get y01 and then y11, okay? That's for the other recursive call. And now you match up this value with that value and this with that, right? So then now you're going to get 4 values, like y0, and now this is again going to be the sort of the 0 side. Okay, that's again going to be the first recursion, and then this one is going to be the 1 side, which is the other recursion. Okay, so that's why I'm going to write this as y00 again, right? But these 2 values are not equal to each other, right? But I'm just going to sort of reuse this notation. Okay, so then this is this is going to be y10, y20, y30. And here you're going to get y01, y11, y21, and then y31. Okay, and then finally to combine these, you're going to match up the first value with over here and the second value over there, and so on. Okay, so the reason I'm showing this in such detail is because later on when we actually implement this in parallel and so on, right? We're going to need to see exactly which values get matched to which other ones. Okay, so it's useful here just to sort of clearly show which values are being matched up with each other as we as you compute this step, right? So all right, so that is the recursive FFT. And now, so we're gonna see. So now we're done with the sequential. Oh, one more thing. I need to talk about the order that these these values appear in. Okay. So if you look at the order of the final level of the recursion, okay. So the order is like A0, A4, A2, and so on. Right. So so what is this order? Okay, it's definitely not the original order A0, A1, A2, and so on. Okay. So it turns out that this order is actually what's called the bit reversed order. Okay. So what happens is now if you write out these coefficients, sorry, these indices, okay, in binary. In binary, okay, so then here you have basically you have 0 is 0 0 0, right? This is 1 1 0 0, right? This is 0 1 0, right? This is 1 1 0. This is 0 0 1, right? This is what is this 1 0 1, right? And then this is 0 1 1, and then this is 1 1 1. Okay. Now what is this order? Now suppose you take each of these binary representations and then you reverse all the digits. Okay, so for example, if you take the 1 0 0, right, you're going to change that, right? You're going to change it to 0 0 1. Okay, you simply swap the you just reverse all the digits. Okay, right? So this one doesn't change, right? But then this one would become like 0 1 1, and so on, right? So if you let's just do all of these. Okay, so this is 1 0 1, this is 0 1 0, this is 0 0 0, 0 0 0, this is 1 1 0, and this is 1 1 1. Okay. So now, if you look at these bit reversed indices, okay, now these actually are the binary numbers just listed in order, right? Okay, so so that means that these this ordering on the final values that you're sort of matching up, okay. So this is just the bit reversed order from the natural set of binary from the natural sequence of binary numbers, right? You take these binary numbers, you reverse all their bits, and then you get this sequence of numbers on the bottom level of the recursion. Okay, so so now we've seen this recursive formulation of FFT, right? But that's still a sequential algorithm. So now we're going to get to some parallel implementations of FFT. Okay, so the first parallel implementation is going to be based on circuits. So the circuits, this is not like a real computer. It's something that you could actually build in hardware, the circuit thing. Okay, so the way it works is that we're gonna build everything based off of this very basic circuit over here. So what this circuit is gonna do, so this is called a butterfly circuit. Okay, so it's just gonna take two inputs, right? Actually, it's gonna take like three inputs. Okay, so it's gonna take this y0 and y1 value, and then all it's gonna do is output this value over here and this value. Okay, so it'll take y0 plus this other value over here times the y1, right? And then it'll take y0 minus this other value times y1. Okay, so that's all it does. So that's our basic circuit. And now we're going to combine these circuits together in a way to compute the FFT. Okay, and so basically what we want to do is, so we saw the recursion tree for the FFT. Okay, so we're going to use these circuits in order to implement this recursion tree. So for example, at the very bottom level here, okay, so what we want to do over here is just to take A0 and A4 and then we want to combine them. Okay, so how do we combine them? Well, right, we should combine them in this way. Okay, so we have this A0 value over here, right? And then we should, we have the A0 value, we should multiply by this omega. So at the very bottom level, the omega is just going to be 1, okay? And so we should take A0 plus A4, okay? That's this part over here, right? And then we should also compute A0 minus A4, okay? And so that's going to produce these two numbers over here, okay? So it's going to produce the y00 and then the y01, okay? And then likewise over here, you should compute A2 plus A6 and then A2 minus A6, right? So to implement that, we just need to make sure that we're going to match up, because the input here is going to be A0 and A4. So we're going to match up A0 and then A4 over here. Okay, and then we're going to have this value, which is equal to 1, right? We're going to feed these through our little butterfly circuit, and that's going to add one of them and then subtract on the other side. And it's going to produce these two outputs over here. Okay. Likewise, we're going to do A2 and A6. So we have A2 and A6 being fed into one of these butterflies, right? We have A1, A5, and then A3, A7. Okay. So yeah, so these four butterflies are going to implement the bottom level of the recursion. Okay, so so then next we need to take let's see. So this is going to produce two values here, right? So we said that this is 0, 0, and then y1, 0, right? And then this is y0, 1, and then y1, 1. Okay, and we said that now we're going to take these two values and match them together, right? And then these two values and match them together. And what we mean by match them together is that so the matched values are going to go into one of these little butterflies over here. Okay, so then that is so then what we're going to do is you know, this value over here, right? That is the that's the y00 value, right? This is going to go into this butterfly, and the matching value is this thing coming from A2 over here, right? And so that's going to go into the other butterfly, and then the A4 and A6 get matched. So where do we have that? So we have the A4 over here, which is going to get fed into this butterfly, right? So this sort of circuit sort of goes underneath this part over here, and it's actually the input to this one. And then the A6 is the input over here, okay? And then likewise, you have A1, A3 being matched. So we have A1 going over here, and then we have A3 going over here, right? And A3, A7, I'm sorry, and then A5, A7, right? So 5 is going over here, and then 7 is going over here, okay? Yeah, so then this second stage over here, right? This is implementing, you know, this is implementing these two conquer stages, okay? These two combining stages, okay? And then finally, we need to have to do the final conquer step, right? We're gonna match, you know, these values, the A0, you know, these two values, and then these two values get matched up, and so on, right? So you see that, you know, here we're gonna take the A0 value, and then the other input is gonna be the A1 value, right? Because we're matching the A0 with the A1, right? And then the A2 with the A3 is gonna go, where do we have A2? So we have A2 over, let's see, A0, A1, A2, A3. Okay, so then we have the A2 over here, and then we have the A3 over here, and so on. Okay, right, and so that's going to implement the second stage, or sorry, the final stage over here, stage 3. All right. Okay, so this circuit exactly reproduces this recursive formulation of the FFT, right? And all of these stages can be run in parallel. Okay, so each stage does multiple operations, but these operations are independent of each other, so we can do all of these stages in parallel. So in total, we just need 3 stages, right, for 8 values. And in general, if you have n values, right, then this recursion tree is going to have log n levels, and so for your circuit, it's also going to have log n stages. Okay, so this is a parallel circuit for computing FFT, which runs in time log n. All right, so so next we're gonna see how to actually implement FFT on a real computer. Okay, so so the circuit is not really we don't have any architectures, any computer architectures that exactly implement the circuit, but now we're gonna look at how to implement FFT on like a traditional parallel architecture. Okay, so so again, we're gonna be looking at which values we're gonna match up when we compute this these FFTs recursively. Okay, so this is still going back to this recursive formulation where you know, you have these values that you need to match up and then do this butterfly operation on. Okay, so the key is to figure out which values are being matched up. Okay, so all right, so then here we see that in general, so what is the rule for figuring out which processes to match up? Okay, so the rule is that basically if you for example here, right, we're going to match the zero value, the zero value with the eighth value, okay? And you see, so we're matching up this value with that value. And so you see that these two guys, they only differ on the first digit, right, on the most significant digit, okay? And likewise, we're going to match up the 1 value over here with a 9 value. And again, you see that they only differ on the most significant digit, okay? So yeah, so we're now so this is called the binary exchange FFT algorithm. Okay, so it's also going to do if you have n values, it's also going to do log n stages. Okay, at each stage we just need to match up certain values and then do this butterfly operation on them. Okay, so now in the first stage, the values that you match up, you see that to find which values to match up, you simply take a value and then you flip the most significant bit, and that's who you match with. Okay, like for example, this 5 over here, right? If you flip this bit, right, then you're going to get 13. And so you see that x5 here is going to get matched to, let's see, to 13 over here. Wait, did I do that right? I think I drew that incorrectly. So I didn't follow my line carefully enough. All right. Okay, right. So it's going to get matched to this 13 over here. Okay, so so in the first stage, for the m equals 0 stage, right, the nodes that you get matched with are the ones that differ on the most significant bit. All right. Now for the second stage, right? Again, we're going to be matching up certain processes, but now the rule for which guys get matched up is now you're going to look at the second most significant bit, and that's who you get matched with. So, so for example, you know, this guy over here, right? If you flip the second most significant bit, right? So this is going to become a 1 over here. So then x3 is going to get matched to x7. Okay, so you see that here, x3 gets matched to x7. Okay, so in general, that is the rule. Okay, in the m equals 2 stage, right? You're going to use the third most significant bit, right? So you get matched to whoever whoever it is that flips the third most significant bit. Okay, so for example, you know, this guy over here, right? So if you flip the third bit over here, you're going to get a 0, 1, 1, 1, and that is what, 7. Okay, so then this guy is going to get matched with 7. All right, and then in the final stage, you just flip the final bit, okay, the least significant bit. Okay, so that is the binary exchange FFT algorithm, and now so now we can implement this in a parallel setting. Okay, so let me just erase all this stuff because we don't need it. So now suppose you have P processors, okay? So we're doing m-point FFT, and let's say that you have P less than n processors. And for simplicity, assume that both n and P are powers of 2. Okay, so now let R be the log of n, okay? And then let D be the log of P. So what we're going to do is we're just going to split these m points evenly among the P processors. So we're going to give n divided by P values to each processor, right? And then each processor will also produce n divided by P output values. Okay, so in total, this is going to run for m-point FFT is going to run for log n time. Okay, so therefore they're going to be R stages of computation. And yeah, and so we said that in this binary exchange FFT, the communication or the operation is going to be between processors whose ID, or sorry, right, it's going to be between indices whose ID differ in the ith bit. Okay, but this is also the same as processors who whose ID differ in the ith bit. Okay, because for example, these two, these 4 values are going to get mapped to the first process, right? And then these are going to get mapped to the second process, and so on. Okay, so you see that if the value, right? So for example, this value, this gets matched to 1001, right? So if the values differ in the most significant bit, then the processors, so here the processor is going to be 0, 0, right? Here the processor is 0, 1. Here it's 1, 0, and then here it's 1, 1, right? Then the processors also differ in the most significant bit. Okay, so therefore in the ith stage, so here I should say that yeah, so this is going to be I less than or equal to d over here, right? In the I stage, the are going to these processors are going to communicate. Okay, so so you see that once we're so here d equals 2, right? And you see that once we're past the second stage, then we continue to have these butterflies, but this is being done within a processor now, right? Because the first processor is responsible for the first 4 of these values, right? So in the first stage, you need to actually communicate with, processor 0 needs to go talk to processor 2, right? Because that's who you do the that's who you do the butterfly with, okay? And then in stage 1, right, this guy needs to go talk with processor 1. But then in stage m equals 2 over here, right, this when you do this butterfly, all of these values are already sitting on processor 0. So you don't need to do any more communication, right? And the same for all of these subsequent stages. So the only communication is during the first d stages, where d is equal to log of p. Okay, so there we have communication in the first d stages, and then no communication in the last r minus d stages. Okay, so that's the binary exchange algorithm. So now let's see how efficient this algorithm is on different types of parallel hardware architectures. So first of all, let's look at a hypercube. Okay, so in a hypercube, when you have p processors, right, where p is equal to 2 to the d power, then each processor is connected to d other processors. Okay, and these d other ones are the ones that differ in each of the digits of the ID of this processor, right? So if this processor is like X, right, then if you write this ID in binary, right, then if you flip each digit, those are exactly who this processor X is connected to. And now, if you go back to this, if you look at this binary exchange algorithm, the only communication is between, so the way you determine who you need to communicate with is exactly that you take each of these digits of the processor ID, right, and then you flip them. Okay, so in the first stage, you flip the first digit, right? In the second stage, you flip the second digit. Okay, so if this were so if you had a d-dimensional hypercube over here, right, then you would do d stages of computation, and then you would be flipping these d different bits. Okay, so this means that whenever you communicate with somebody in this algorithm, okay, so this comes from flipping the bit, but then this also means that the communicating processors are just neighbors of each other. They're directly connected to each other, right? Like for example, 0, 0 and 1, 0 in the hypercube, they're directly connected because they only differ in 1 bit. Okay. All right. So in general, you can see that so we have d stages of communication in the algorithm. And for each stage of communication, you only need to communicate with a neighbor, okay? And when you communicate with that neighbor, you actually need to send n divided by p values. Because, for example, you see that the first processor, he's responsible for all 4 of these values, okay? And he's actually going to send all 4 of these values over to this guy over here, okay? And likewise, in the second stage, right, he's got these 4 values, and he's going to send these 4 values to this processor, okay, to 0, 1. So each stage you communicate with a neighbor, and then you send all of your values. And you have n divided by p values. Okay, and then we do this for d equals log of p number of stages. Okay, so therefore the total amount of communication is for each stage it's just going to be ts plus tw times n divided by p. Okay, because you're talking with a neighbor and you're just sending that many values. And if you do this for log p rounds, then the total communication time for each processor is going to be this expression over here. Okay, now each stage also does n divided by p amount of computation, right? Because let's see, every time you get one of these values, okay, so like if you clean this up a bit, okay, so if you take these values and you send it over here, right, and then oops, not over here, right, and then this guy sends these values and sends it over here, right? So you just need to, every time you get a value, you just do this butterfly computation, right? This you add the value and then you subtract the value. Okay, so it's just a constant amount of computation for each value that you get. And so, so each stage also does, for each processor, in each stage, it does n divided by p amount of computation. And because there are log n stages in total, then the total computation for each processor is going to be this, okay, n divided by p times log n. And this tc is the amount of time to do one computation. Right? Okay, so now we want to look at how efficiently we can implement this on a hypercube, okay, because we have computation over here, and then we have communication over here. Okay, so we want to see how much of the total time this communication overhead is taking. Okay, so the efficiency is just going to be the computation time divided by the total time, right? The computation plus communication time. Okay, and if you just plug in everything over here, right? So you just take these two TP and TC expressions and you plug them in over here, you get this thing. Okay, so now it turns out that for convenience, we're going to define this term k over here. Okay, so k is basically it's kind of like it's related to e in this way. All right, so we're going to define k by this expression. And now so as you vary p, okay, so that's going to help you go faster, but it's also going to increase your communication. So if we want to maintain the same efficiency, so ISO efficiency, as we modify p, okay, then we have to make sure that these two terms in this denominator do not change as p goes up. Okay, so then n would also have to increase in order for these for the two terms to stay the same. Okay, so suppose you want the first term over here to stay the same. Okay, so suppose you want this to equal 1 divided by k over here. Right, so this is why, so this 1 divided by k over here is basically supposed to capture these two terms, okay? Right, so now if you want this, first part here to equal 1 divided by k, okay? So then what that would mean is, so you do some algebra, and then you see that this is what you need to have happen, okay? So n log n is basically proportional to p log p times this additional factor over here, okay? Yeah, so this shows you that as p increases, you need to have n also increase in order for these two things to stay equal. Right, now for the second term, right, you also don't want that to increase. So you want, as p increases, you want this term to stay the same. So let's say that you want this to be equal to 1 divided by k, right? So then you, again, you do some computations over here, and now you get that n has to be equal to p to some power, okay? And this power is going to involve this k term, and then the so this is the time to send one word divided by the time to do a computation. Okay, so it's basically like your communication rate compared to your computation rate. Okay, so then yeah, and then so you you do some okay, so then w here is equal to n log n, right? So we have this expression for n over here, and the total amount of work, right? So the total work is going to be n log n across all of the processors, okay? Right, because you have n stages over here, right? Or sorry, you have log n stages, and then each stage involves n amount of work, right? So if you look at the computations that's being done, every single value needs to be involved in some computation. So there are n values, so there's n amount of work in each stage times log n stages, okay? So so therefore w here equals n log n, and then we have that, so we have this expression for n, you plug it into w, and you get this thing, okay? So as p increases, the total amount of work needs to be this size in order for us to maintain the same efficiency. Okay, so yeah, so then this, so what we need is for w to be at least this large, right? And also w needs to be at least this large. Okay, so w is going to be at least the max of these two things for ISO efficiency. And now what this plot is showing is that if you want different degrees of efficiency, okay, then suppose you increase your number of processors. Then according to this equation, your total amount of work also needs to increase, right? And in fact, So this plot shows that for different efficiency levels, how quickly does your amount of work need to increase? Okay, so so basically, like here, if you're shooting for a low efficiency, okay, so then you can plug this 0.2 in for here, and you can get a value for k. Oh, I'm sorry, I forgot to label these. So this is for yeah, so this is for a certain setting for these TC, TW, and TS parameters. Okay, so I forgot to add those in here, but I'll do that later. Okay, but for a certain value, so you see that this work here involves these parameters, right? So the TS, right, the TW, and the TC. Okay, so for a certain setting of these, and for a certain setting of E, you're going to get a K value, and then if you plug that in, right, then you're going to get these different plots. So the upshot for the plot is that as you want higher and higher efficiency, right, then your problem size has to grow with the processor count, and it's got to grow very, very quickly. Okay, if you just want to shoot for low efficiency, your work has to grow with the processor count, but not very quickly. But if you want much higher efficiency, right, then the work is going to grow much more quickly with the processor count. Right? So in particular, it's going to grow like this. Okay, so it's going to be p to some power, where this power is going to involve k. And as you increase efficiency, then k is going to get larger, and so this polynomial over here is going to get larger also. Okay, so that is the binary exchange algorithm, and then this is the efficiency on a hypercube. Oh, okay, I'm sorry. So these are the values. Okay, so these are the settings for the TC and the TW and the TS parameters. Okay, so now let's see. Let's try to implement this binary exchange, not on a hypercube now, but on a mesh. Okay, so some mesh architectures are easier to build than hypercubes, and so let's see whether we can implement this binary exchange algorithm efficiently on a mesh. Okay, so suppose you have a root p by root p mesh. So you have p processors total. Okay, and let d be the log of p. Okay, so now remember the communication pattern that we had. Okay, so so the communication pattern, if we go back to this plot from earlier, right? So let's try to clean this up a bit. Okay, so the communication is when you have let's say n values. Okay, so in the first round of communication, you need to talk to the value. You need to do a butterfly with a value that is n divided by 2 distance away, right? So here you have 16 values, and you have butterflies between values that are distance 8 from each other. Okay, and in the next stage, you have butterflies between values which are distance 4 from each other. Okay, and then 2, and then 1. Okay, so you see that the distance of the value that you need to communicate with, or sorry, that you need to do the butterfly operation with, right? This is starting at n divided by 2 and then decreasing exponentially. Okay, so that means that when you're talking about the mesh, okay, now suppose initially we distribute the values this way. Okay, so we have, so we're trying to do, let's say, a 64 point FFT over here, right? And we're just going to distribute the values row-wise. Okay, so now that means that in the very first stage, right, the 0 value needs to talk with a value that's 32 away. In the second stage, the 0 value needs to talk with a value that's 16 away, right? And then 8, and then 4, and then 2, and then 1. Okay, now let's see where these values are located on the mesh. Okay, so if you distribute the values this way, then you see that for the first 3 stages of computation, right, we're talking with 32, 16, and 8. And because there are 8 values per row, then this means that all of these values are on the same column as this 0 value. Okay, so 0's communication is initially with the values that are on the same column. Okay, and then after the 3rd stage, it's going to be communicating with 4, 2, and 1, and these are going to be on the same row. Okay, so yeah, and this actually holds for any process. Okay, so for example, 37, initially it needs to talk with somebody who is distance 32 away, right? So 37 plus 32 is 69, right? But then you need to take that modulo 64, and so that's 5. Okay, so initially 37, value 37 and 5 are going to do this exchange, a butterfly exchange. Okay, and then you talk with somebody who's distance 16 away, who is over here, and then distance 8 away. Okay, so for the first 3 stages, the communication is just along the same column. And then after the third stage, right, you're going to talk with somebody who's distance 4, and then 2, and then 1 away. Okay, and those are going to be on the same row. So this just shows that for every process, for the first, so if you have d equals log p over here, okay, then for the first d over 2 rounds, the communication is going to be with the processors in the same column, and then for the next d over 2 rounds, for the last d over 2 rounds, it's going to be with the processors in the same row. Okay, so again, you have if you have d equals log p, then again you're going to have just d rounds of communication. Okay, you could have so you could have n is larger than p. So so in that case, the total number of stages that you run is going to be let's see. So if you define r equals log of n. Okay, so in total you're going to run for r stages of computation. Okay, but you're only going to have d equals log p stages of communication, because once you're so this is going to be in general larger or equal to that, right? Because once you've done the first d stages, then after that all of the communication will be within a processor itself. Okay, so right, so as we saw with the right, so you see that once you're past stage what is it, stage D over here, right, then the communication is just within a processor. Okay, so then right, so then we have that we have this communication pattern first with the guys in your column, and then with the guys in your row. Okay, now when you're doing this column-wise communication, let's see. So the distance of the node that you're communicating with, okay, is going to be like this. So for the first d over 2 rounds, we're communicating with the guy in the column, and the distance is gonna decrease, right? So initially, it's just going to be 2 to the d divided by 2 distance. Okay, initially it's sort of like halfway down the column, and then a quarter, and then an eighth, and so on. Okay, and the same thing for the rows. Okay, so and this is happening for all of the processors in the column. Okay, so in the first round, right, this guy is talking with this guy, right? This one is talking with that one, and so on. Okay, so so because it's happening with everybody, then if you you know, we have these edges in the mesh, right? Okay, so then if you look at one of these edges, well, you have a lot of paths that are crossing this edge. Okay, so for example, this edge over here, right? Well, this communication needs to use this edge, right? And then this communication is going to use the edge. So all of the communications are using that edge. So you have a lot of congestion on certain edges. Okay, and in fact, because you're communicating this distance away, okay, you can see that the amount of congestion on a edge in this column is also going to be this in the nth round. Okay, so the congestion does decrease as the rounds get larger, right? However, for the initial rounds, you're going to have a lot of congestion on these column edges. Okay, and then once you get to the communication among the rows, right? Then again, for the first few row communication rounds, you're going to have a lot of congestion, right? And the congestion decreases over time because over time you communicate with nodes which are closer to you, and so you have less congestion. Okay, but you have this type of congestion. And so, so once we have this, then now we can compute how much time it's going to take to implement this on a mesh. Okay, so the computation time is still going to be like this. Okay, so every so you do log n stages. Every stage you do n divided by p computation. Okay, so so you can see that here all the computation is perfectly load balanced, right? Because the total amount of computation is n log n. And here each process does exactly that thing divided by p. Okay, so the computation is balanced. Then for the communication, right? So this is the communication time. Okay, So the communication time is basically, the startup time, and this is the amount of data that you're sending, right, times the per data time, okay? However, this part here is the congestion, okay? So we said that this congestion is very large initially, okay? So if you add up the congestion over all the rounds, this is what you're going to get, okay? And this is going to simplify to, so m is going to range from 0 to d over 2. Okay, so so we have d is equal to log p, right? So therefore 2 to the d over 2 is going to be root of p. Okay, and so so this whole thing is going to simplify to something like this. Okay, so basically n divided by root p over here. All right, so now in terms of efficiency, so this is going to be the computation time divided by the computation plus the communication time. Okay, so if you do that, if you simplify everything, right, so you get, yeah, you're going to get, let's see, how do we get this? So this term is n divided by p. Let's see, so the communication time, okay, okay, right, yeah, so this thing here divided by that, right, that's going to get you this term. Yeah, sorry about that. I spaced out, and then this thing divided by that is going to get you that term. Okay, and again we're going to write this in this form with the 1 over k thing here. Okay, and so now if you want to maintain the same efficiency as the processor count goes up, okay, then you need both of these terms to stay constant, and this is not such a problem. So as p goes up, then you can just take n larger, and you can maintain this to be a constant. Okay. But this is a problem because as p goes up, right, so then this root p thing is increasing pretty quickly, right? But then you see that here you're going to need, for example, if you make p 4 times larger, then this thing is going to double, right? But then here, if you want to make this thing, double, right, you're going to have to square n, right? So basically, here this n term is going to have to increase a lot faster than this p term in order to keep this expression be constant. Okay, so in fact, if you work it out, you're going to see that the work is equal to n times log n. Okay, so the work is going to be something like this. Okay, so this is going to be now exponential in the p term. Okay, so p is now in the exponent of the work. So the work needs to increase very, very quickly as the number of processors goes up. Okay, whereas for the where is it? For the hypercube algorithm, right? You see that here the work only needs here the p is not in the exponent. Here the work is polynomial in p, whereas for the mesh, the work needs to be exponential in p to keep the same efficiency. Okay, and so basically the upshot here is that the FFT algorithm is actually not scalable on the mesh. Okay, and the reason it's not scalable on the mesh is because the mesh has only root p bisection width, right? Whereas you need to do for the FFT, you need to do a lot of communication, right? So you need to do you need to do like a linear amount of communication in each stage, right? Because here, like you see that you need to take all this data and send it to another processor. Okay, so here there's like a linear amount of communication in each stage. And the mesh cannot keep up because it only has root p amount of bandwidth between the two halves of the mesh. Okay, so okay, all right. So yeah, so now we're going to talk about one final FFT algorithm. So this is going to be called the 2D transpose algorithm. Okay, now. So the 2D transpose is, we're going to run this thing on the hypercube, okay? But we're trying to improve the efficiency compared to the previous binary exchange algorithm. Okay, so remember that the binary exchange algorithm had the ISO efficiency depended on this value over here, okay, this k times tw divided by tc. So when this value is small, right, then all you need is the work to increase at this rate, okay, at p log p. However, if this value here becomes larger, right, then this thing goes into the exponent over here. And so if this is very large, then you need the work to increase much faster. Okay, so yeah, so this basically shows that if this value is large, then your efficiency is going to degrade. So instead, if you look at the 2D transpose algorithm, right, this is always going to have this p squared log p efficiency, okay, regardless of this parameter over here. Okay, so if this parameter here is small, then the binary exchange algorithm is actually better, right, because then the isoefficiency is just p log p as opposed to p squared log p. But if this thing is large, right, and in practice this can be large because TW is usually much larger than TC, right? So this can be quite large in practice. So in that case, the 2D transpose algorithm is going to be better, okay? Because this doesn't care about your machine parameters. It's always going to have the same isoefficiency. Okay. So this thing is we're going to run this on a hypercube, but you can also run this on a different architecture with as long as it's got a bisection width of order p. So for example, the fat tree, you can also run this algorithm on. Okay, so we're going to assume that root n now is a power of 2, okay? And we're going to arrange all of the input values in a root n by root n grid. And the way the algorithm is going to work is that, okay, so initially, so for example, if you have 16 values, okay? So we know that in the first stage, you need to do exchanges between values which are 8 apart, okay? So 0 and 8, and then 1 and 9, and so on, okay? So you see that if you arrange the values on this grid, right, then you're only doing communication among the columns. Okay. Now in the second stage, you're going to communicate with nodes which the communication is between values, or the butterfly exchange is between values which are 4 apart. Okay. So then again, you see that the butterfly is between values which are on the same column, right? 0 and 4, or 1 and 5, and so on. However, once you move to the third iteration, right? Then the communication, then the butterflies between values which are 2 apart, then they're going to be on the same row now, right? And in the fourth stage, they're also going to be on the same row. Okay. Now for the 2D FFT, our goal is going to be that. Well, okay, so let's do it this way. Okay, so we're gonna arrange first of all the values in this grid, in this root n by root n grid. Okay, and then let's say first of all that you have exactly root n processors. Okay, then we're gonna assign 1 processor for each column. Okay, and so you see that in this 2D FFT for the first two stages. Because you're only communicating within a column, right? Like between 0 and 8, or 1 and 9, and so on. Sorry, the butterflies are within the same column, okay? Then there's actually no communication that we need to do because each processor has an entire column of values. So this butterfly between 0 and 8, this is happening on the same processor, right? This 1 and 9 thing is also happening on the same processor. So in the first stage, we actually don't have any communication. In the second stage, the butterfly is again within the same column, right? So again, we don't have any communication. Okay. Now in the third stage, previously we had butterflies between on the same row, right? And so if we assign processors to columns, then in that case, we would have communication between different processors. Okay. However, the trick to the 2D transpose algorithm is that before we start the third stage, we're going to transpose all of the values. Okay, so that means that we're going to take these columns and make them into rows, and then the rows are going to become the columns. Okay, so for example, this row becomes the first column. Okay, so we're going to transpose everything. And so that means that before the transpose, we were going to do communication within a row. But now after the transpose, we're going to do communication within a column again. And now the column, right, everything on the same column is going to be sitting in the same processor. Okay, so then again, we don't have any communication here. Okay, and then in the final stage, right, we again do butterflies between processors which are between values which are 1 apart, but then those again are going to be sitting on the same processor. So again, there's no communication. Okay. So the only communication was in this transition when we had to transpose the values to go from this configuration to the transpose configuration. Right. That was the only step where we had communication. Okay, so this was where you have the same number of processors as you have columns. Okay, now in general you could have less processors than columns, and in that case you can just divide the columns evenly among your processors. Okay, so for example you can use a striped format. So so here you have 4 processors, right? And you assign the columns to the processors like 1, 2, 3, 4, 1, 2, 3, 4. Okay, but when you do this, you can see that still you only have this one time when you need to communicate to do the transpose. Okay, right? Because otherwise, all of these values are sitting on the same processor. Okay, so so now we can go figure out the efficiency of this algorithm. Okay, so all we need to we're going to look at the computation cost, and then for the communication, it's just going to be the cost to do the transpose. Okay, so first of all, the computation. So now if you have P processors, right, then each processor is going to be responsible for root n divided by P columns. Okay, and each of these columns has size root n. Okay, so you can see that the computation it does for each stage is going to be the product of these two things, right? And then there are log n stages, and so the total computation is going to be this. Okay, it's just going to be n log n divided by P. Okay, so it's again it's completely load balanced. And then the only communication is for the transpose. Okay, so for the transpose, if you go back to one of our earlier lectures on doing collective communication, right? So here we need to do the all-to-all personalized communication. Right? That's how you do the transpose. And whether you do this on a hypercube or any other architecture which has theta p bisection bandwidth, then you're going to see that it's going to take this much time. Okay, because each time you're sending this amount, each process is sending this amount of data, right? And you're doing all-to-all personalized, where each process has that amount of data, and so this is the amount of time you're going to take. Okay, so then now if you look at the efficiency, it's just going to be the computation time divided by the and the communication time. So you have these two terms. You have the computation divided by this term, and the computation divided by that term. Okay, and so so it's going to come out to this, right? So we want both of these terms to be constants, and so in order for the first term to be constant, you need n log n to be at least as large as n squared, right? And then for this other thing to be constant, okay, well this just decreases with n. Okay, so we can sort of ignore that term. Okay. And all right, so we also have that root n has to be at least as large as p. Okay, because you can't use more processors than columns, right? In this algorithm, you can only have as many. The maximum number of processors is the number of columns that you have. Okay, so therefore you have that n is going to be at least p squared, has to be at least p squared, and so the total amount of work w is n log n, and so this needs to be at least p squared log p in order to maintain ICE efficiency. Okay, so so this basically says that so we have this transpose algorithm, and in most scenarios it will be better than the binary exchange algorithm, unless you have like a very fast, unless you can achieve very fast communication, right? So if this TW here is very small, then the binary exchange is actually going to be more scalable than the 2D transpose. Okay, so that's all we have for this lecture. I'll talk to you guys next time.